have been introduced to terminology called synthons, and I've shown you how you can disconnect a molecule, which will give you some synthons. And in this video series, we are going to talk about synthons and how you can actually get synthons from disconnection. Okay, if you look at the first example here, okay, this is your target molecule. So let's say we disconnect this molecule at this bond, yeah. Okay, and then the second molecule we disconnect in the middle of the molecule, and in the third target molecule we disconnect the bond through the bond between carbon and nitrogen. Okay, let's see what synthons that you will get after you disconnect the bond. Okay, in the first molecule, what we can see, if we disconnect at this part, normally when we disconnect those bond that is near to the functional group. Okay, so let's say we disconnect at this part. So we get plus, or this one plus and also minus. You can also have another pair, which is this. Okay. You can also have this one, and the partner is this one. Okay, so these are two sets of synthon. This is the first set, this is the second set. Okay, let's take a look at the second molecule here. Okay, when we break the bond in between, so we get the first fragment is this part become minus. Okay, this is the first pair. The first pair where this is minus and then this is plus. Okay, you notice that this bond is no longer there. Okay, because it has been disconnected, so this middle bond is no longer there. So another pair can be this one. Same thing, CO2 ET here. But the difference is this is become plus, and then another one become minus, for example. Okay, so let's take a look at the third molecule. Okay, so when we cut the molecule here, which means we no longer have this bond. Okay, we no longer have this bond. So it becomes a plus and minus, or you can have another set, which is this. Okay, this become minus, and also this become plus. Okay, so these are the synthon, yeah. Okay, let's take a look at when we already have a synthon. So what is the real synthetic equivalent? Okay, let's see here. If we have this synthon, okay, so when it is plus, you know that when OH, the next carbon is plus, so it will be converted into a carbonyl compound like this. Okay, if carbon is plus, then the next functional group is OH. The real synthetic equivalent are most likely aldehyde like this. And then when you have when you have negative charge like this, it needs to be complemented by something positive. So that something positive is MgBr. Okay, it become Grignard reagent react with aldehyde. Okay, this is a very sensible reaction where you know that These two starting material can produce this compound. Okay, let's take a look. This is the first pair of synthon. Okay, let's take a look when we have another pair that we draw just now. Okay, so this is OH. So what if it is minus? And then this is plus. Okay, let's say we have this pair. So we want to make a synthetic equivalent for this. Okay, if this is minus, you need to balance it with something positive, for example. Okay, let's say something positive means maybe you can add hydrogen, for example, because hydrogen is positive. Okay, now we have plus. So plus is maybe you can complement it with Cl. But if you look at this reaction, can you think of reaction that is suitable for this synthetic equivalent? So which one will be the nucleophile? So which one will be the electrophile? If this kind of reaction, you already know that a Grignard reaction, the nucleophile is this part, the alkyl part, yeah? So it will attack this carbon and the bond will move. But what about this reaction? Okay, if you cannot think a suitable reaction, then it is suggested that if you have two sets of synthon like this, so this one is the best pair because the synthetic equivalent represent the known reaction. Okay. Okay, now take a look at the second example here, second molecule. Okay, when you have this one as your synthon, okay, when it is minus, so you need to balance it with hydrogen. So it becomes this compound. It is a diester, and then you have a double bond here. A double bond here. It is plus, so it is complement by bromine, which is negative. So in this kind of reaction, you can think that this Br can be made into MgBr. Okay, you can make it become this. You react with Mg, so you can get Mg ether. So you can get a Grignard reagent. Okay, Grignard reagent. So this Grignard reagent then can attack the ester. Yeah? Okay, this is a reaction of Grignard reagent with ester. Okay, let's take a look at another pair. Okay, when you have another pair, so I draw it here. Another pair just now, when you have this is plus. This is the R lah, R group. And then the other one here is minus. Okay. Okay, now, when we want to, let's say it is plus. Okay, we want to complement, for example, let's say because it is plus, we put Br there. We put Br to complement the plus. But, does this molecule exist? Does this molecule exist? So, is it exist? And then, the question is whether this molecule exists. And then, another one is, when you want to complement the minus, you need to add hydrogen. So between this molecule, which one is the nucleophile? Which one is the electrophile? And then when you have this kind of molecule with Br, normally this compound is not readily available starting material because it has so many functional groups in there. And even if you want to purchase it, even if it is available, if you want to purchase it, then it will be very expensive compared to the first alternative here. Okay, that's why this is the best pair of synthon. Okay, and then we have this third molecule. Okay, this third molecule, okay, as usual, when we break this bond, so this bond is no longer there. Okay, so you will have plus charge there, plus and minus. Okay, you still remember the other pair is this one? Okay, this one is minus, and then this one is plus, for example, plus. Okay, the first pair here, the synthetic equivalent is acid chloride. Because this is plus, you can complement it with chloride, which is negative charge. Then because this is minus, you can add hydrogen. Okay, in this kind of reaction, the nitrogen is the nucleophile. So what happened is that this nitrogen having lone pair electron will attack this carbon. Then this bond will move to the oxygen. And then what happened is that this will be broken. So it will give you an amide compound like this. Okay, let's take a look at the second pair. Okay, the second pair, if we have minus just now, so we want to complement it with, okay, let's say we have minus. Okay, because it is minus, so maybe we can add hydrogen, for example. Then hydrogen, and the second synthetic equivalent is, let's say, because it is minus, so because it is positive, so we need something minus. Okay, let's say we put chlorine. But does this compound, is it exist? Does this chlorine, nitrogen with chlorine compound, does it exist? So if there is a question of that, so even if it is exist between these, which one is the nucleophile? Okay, even if you say the lone pair of this oxygen can attack this nitrogen, and then the bond will leave. But is that reaction really feasible? So in that case, this reaction is a lot better. So this is the best pair of synthon. Okay. Now we can have, you can take a look of some common donor synthon, which is the carbon nucleophile here. Okay, for example, if you have AR minus or RR minus, so the synthetic equivalent can be a H, or this minus can be complemented by hydrogen or M or metal, such as lithium, magnesium bromide, copper, organocopper. And then if you have like this uh, carbon carbon minus, so you can complement it with M, which because M is plus, and then this one also you can complement it with M. And then when you have alkyne like this, okay, you can complement it with M as well. Then if you have ester like this, okay, or if you have ether, or if you have CN, there is always some synthetic equivalent, yeah. Okay, and then if we look at another example of synthon, for example, this synthon, you can get something like this, where this Mass CO meaning it can be converted from the aldehyde. And then let's say if you have another synthon like this, so minus means you add another hydrogen, so it will give you this one, or you can get an ester like this. And if you have minus, so minus can be complement with um, some functional group, and then also these are sort of donor synthon, yeah. Okay, for acceptor synthons, these are some of the common acceptor synthons, and the difference between donor and acceptor synthon is the charge of the synthon. So in acceptor synthon, the charge are positive. Okay, let's say you have this compound, the AR plus, so the synthetic equivalent can be ArN2 plus. In the second one, you see if you have plus at the carbon, so you need to complement it with something negative, which is hal. Hal here means the halogen, because you know halogen is negative 1 charge. And then if you have another synthon here, which like I said before, if you have carbon next to OH and it is plus charge, so the synthetic equivalent will always be a carbonyl. This C plus OH will turn into C double bond O. And then if you have C double bond O with plus, so you need to complement it with something negative to neutralize the molecule. So you can use X, or X either it refer to halogen or OET, yeah? OET group. Okay, next if we have double bond O, OR with plus, so you can either complement it with X, so anything negative, or you can just convert the whole thing into CO2. Okay, then another one, which when you have a synthon, that the carbon is plus, but this is not the carbon that next to the OH, yeah? If the carbon plus is next to the OH, it becomes carbonyl. But if the carbon is the next carbon, which is plus, it will give you an epoxide like this. Okay, if you have R, because this plus means it is CH2 plus, yeah? Plus. Of course, when it is plus, you need to complement it with halogen. So that's why this is CH2. Then you need to add X, okay, which is the halogen. And then if you have an ester with plus like this, so plus can be complement with Br, so it is CH2 Br. Okay, so this type of molecule, it is not common, and normally when you buy it, it is very expensive because it has halogen and it has also ester group here. Okay, now we have, if you have a ketone, for example, and this one is plus, so this plus, you can, the synthetic equivalent could be alkene, or this can be converted into OMe, 2-OMe with Br atom at the end of the chain. The only way to learn the information presented in this both table is by practicing example question again and again. Yeah? Because without practicing, it is not easy to imagine how you can get a synthon and then how you can get the synthetic equivalent. Okay, okay. When we talk about synthon and disconnection, So how do we choose a good disconnection? Yeah. So below are some of the guidelines. So first point is make disconnection corresponding to non-reliable reaction, as what I have mentioned in the previous slides. So and then the second one is using two-group disconnection, meaning between two C double bond O group or other pair of group. Okay, for example, if we look at example number 1, okay, this example number 1, it used two group disconnection. Yeah. Okay, if you look at here, we have a carbonyl group here and then a carbonyl group here. So what we can do is we disconnect these two molecules. We disconnect in the middle, this part. Yeah. So what we get is a synthon fragment. So this is the plus, this is the minus. So the synthetic equivalent, because this is plus, OET is minus, so you can add OET to complement the plus charge. And then this one is minus, so you can add hydrogen. So this part become Me. Okay, so how do we do this reaction? This is a reaction between ester and ester. So you have learned in the previous learning unit where you can do a reaction between ester and ester, which is called Claisen condensation reaction. So in this case, you have one ester here. So you have a base. So what do this base do is it's going to abstract one of the alpha proton here. Yeah. So CH, then you have another H, then you have another H. So this will abstract one of the proton from the Me, and then this bond will be broken, and then this C will become minus. Okay, so when it become minus, it will move to this bond, and then this bond will be broken, and then the electron will migrate to the oxygen, and then you will get oxygen minus, which then the electron will migrate back to this bond, and then this bond will attack this electron, the nucleophile here will attack the carbonyl carbon, and then this group will leave. So you will get a Claisen condensation compound. Okay, so example 2 is also two group disconnection. Okay, you have double bond O here and you have OH here, so you break the bond in between these two functional group. Okay, so you will get these two synthon minus and plus. Okay, so the synthetic equivalent minus here, you can add hydrogen. Okay, so it is Me. This one you add hydrogen here, so the molecule is now neutralized. And then for this one, because it is, if you still remember what I said, if you have OH and then the carbon next to the OH is plus, so it can be converted to C double bond O like this. So the forward synthesis is using the aldol reaction. So it's the same thing. So you have the base will abstract the alpha proton, and then the alpha proton, what happened is that this will become minus, and then this bond will be the electron from the oxygen minus will move to this bond, and then the double bond, the pi electron here will attack this carbonyl bond, and then the bond will be the electron from the C double bond O bond will move to the oxygen, and then it will give you a minus oxygen here, which when you introduce acid, it will give you this target molecule. So this is the same thing In each case, disconnecting between two functional groups is a simplifying operation, and it is often the easiest way to get back to the simple starting material. That's why it is good when you disconnect between two functional groups, because you can find the suitable starting material to synthesize that compound. Okay, now we have a disconnection guideline, another one. So if a compound consists of two parts joined by a heteroatom, so you can disconnect next to the heteroatom. Because why is it so? Because carbon heteroatom bonds, they are always easier to make, usually by nucleophilic substitution reactions such as alkylation or acylation than carbon-carbon bond. Okay, let's take a look at this example. Okay, we have a heteroatom bonds here. So which one is the heteroatom bond? Is this one. Okay, this is the heteroatom bond where S is connected to C. Okay, this is a polar bond, so it is easier to break. So when you break it down, so it will give you a pair of synthon. So this become minus, this will become positive. Okay, when it is minus, it can be complement with hydrogen. When this is plus, it can be complement by Cl. Okay, when you draw this kind of compound, please make sure you don't draw it like this. Yeah? Let's say you draw it like this. Okay, because you think that that is plus, so you draw it like this. Okay, this is wrong. Because why? If you notice, although this is plus, this is CH2 plus. So when it's attached to the Cl, the bond here is still there. Okay, the CH2 need to be there. But if you just replace it with the Cl, then the CH2 is now gone. And you couldn't get the target molecule as what you imagine. So in this case, the forward synthesis is very straightforward. So you have this synthetic equivalent. So this thiol compound, when you have base, what base do is it abstract this hydrogen and this bond will be broken. So now you have S minus. Okay, when you have S minus, what happens? It will attack to the carbon that is partially positive. In this case, this carbon is the most positive because it is attached to the chlorine, which is an electronegative atom. So S will attack this carbon and this bond will be broken. As you know, chlorine is a very good leaving group. So what happened? You finally form this compound. So it is very easy. Okay, the fourth strategy is you can also disconnect towards the middle of a molecule to make two reasonably equal halves. Okay, middle of the molecule to make two reasonably equal half. Or number 5, you can disconnect at branch points. So this strategy is more likely to give a straight chain fragment. Okay, so if you are using these two strategies, these simplifying operations, they are more likely to give reasonable starting material. Okay, let's take a look at the example here. So, this is a compound with lots of branches. So, you disconnect at the branch point, which is this part. Okay, the branch point. And now, when you disconnect at branch point, okay, this part become positive, this part become negative. Okay, you always know that when you have a C plus next to the OH, it will become carbonyl like this, yeah, or aldehyde. And then when you have a minus, so it can easily be complement by BRMG, MgBr, which is the positive charge. And the forward synthesis is very simple. You have the alkyl bromide, you react with Mg, so it will give you a Grignard reagent. So this Grignard reagent, when you react with aldehyde, so it will give you an alcohol like this, yeah. So you get an alcohol after workup, meaning you need to add some acids, okay, to turn these molecules into an alcohol. So for this part, you might want to refer to Learning Unit 2 on the Grignard reactions. Okay, number 6, disconnection guideline number 6 is you can disconnect back to readily available starting materials. And number 7, use symmetry if possible in a helpful way. Okay, let's take a look at this example where you can use the principle number 7, where you disconnect twice at the branch points. Okay, if you look at this compound is symmetrical, meaning both sides are the same. So since both sides are the same, maybe you can disconnect twice at this branch point. So what you get is pH 2, and in this case pH is, the synthon is like this, yeah, pH minus, and then this one OH, this is plus, okay, Me, yeah. So 1, 2, 3, 4. 1, 2, 3, 4. Okay. So you know that when the C plus is next to the OH, it will become carbonyl. So since you have two sets of Grignard reagent, you know that normally when you have two Grignard reagent, so it will react to the ester. Okay, so if you only have one Grignard reagent, normally it is either aldehyde or ketone. But you know you have two, so it is definitely an ester. So in forward synthesis, what you need to do is the ester you react with the first molecule, the first mole of the Grignard reagent, and then it will give you a ketone, and then this ketone will subsequent reacted with the another mole of the Grignard reagent, so it will give you the target molecule. That's the end of this guideline. So we will talk about the strategy of retrosynthetic analysis in the next video.